Kind of drill down a little deeper into some of the topics that we've already covered and diagram some stuff and talk about the timings and the packets and all that kind of stuff. So everybody's following along okay so far? Everybody good? All right. So troubleshooting DMX, how do you do it? Well, first of all, if you have no DMX signal at all, a lot of times the console may not be patched correctly. So you might want to check your console patching. Also check your Grandmaster fader for blackout. You know, that's I've done that a couple of times. It's like, hey, there's no output. Oh yeah, the Grandmaster fader is off or whatever. Blackout button. Check for what?
Blind mode.
Oh yeah, check for blind mode as well. That's another one. That's one of those gotchas, right? Blind mode, yeah. Now, fixtures also have self-tests, and you can go a long way towards troubleshooting if you just put the fixture in self-test mode. Now, it used to be that you would have to be able to get to the fixture, to the menu, to put it in self-test, but now with RDM, you can actually do it remotely. So you can test out the fixture, make sure the fixture is working. And then check the starting DMX address of the fixture as well. So those are, you know, some real basic kind of things that you might want to check. So in my experience, most of the time, when you have glitches with DMX, it's probably caused by a lack of data termination. Sometimes it's faulty wiring. Ground loops are more rare. And a ground loop is when you have a console and some fixtures that are connected by a DMX cable where the shield is connected on both ends. Now, the way fixtures are supposed to be built, DMX is designed to be what's called a telescoping shield. That means when you connect the cable to the console, pin 1 connects to the chassis, but when you plug it into the fixture, pin 1 is not supposed to be connected to the chassis of the fixture. If it is, then you can get current flowing through the shield and through the power cable around back and forth, and that can cause data problems. In my experience, that's not a super common problem, but apparently it is an issue. So, you know, check the simple things first. Is it terminated? The number of devices on a single link, we'll cover that in a moment. And then obvious problems like bad cabling or missing cabling, that kind of stuff. When you have flicker or flashing, in my experience, the number1 cause of flicker or flashing is lack of data termination. And the solution is very simple, just terminate it. Incorrectly built data terminators. I've had people tell me before, oh, the system was working fine until I plugged in a data terminator. If that's the case, that data terminator is wired incorrectly. The 120 ohm resistor goes between pins 2 and 3. If you solder it between pins 1 and 3 or 2 and 1, then it's not going to work, and you have problems with your DMX. So you should have a 120 ohm resistor between pins 2 and 3 and an open circuit between 1 and 2 and 1 and 3. Question?
I've seen sloppy ones before where they'll get soldered between 1 and 2 or 3 and 4, and then it screws it up even worse.
Exactly. Yeah, so if you have a sloppy soldering job and you get a blob of solder when you're soldering your resistor and it shorts out to the shield, pin 1, then you're shorting out the data signal and it's not going to work well. Yes?
It's also important to know that over time resistors will break down and fail.
Exactly, yeah, so that's a good point that Ray brings up. Ray said that over time resistors can break down and fail. And here's the thing is that resistors have a resistance value measured in ohms, and it's painted and there's a color code. And you can read the color code and tell what value the resistor is. But what's not painted on it is the wattage of the resistor. So the bigger the resistor, the more heat it can handle. Heat is the enemy of electronics. It breaks things down, it deteriorates them, makes them stop working. So DMX signal is not a lot of energy, but a little bit of energy over a long period of time tends to break things down. So the issue is, I mean, if you could put in a 10-watt resistor in that XLR connector, then it would last forever and ever, because the DMX signal is nowhere near 10 watts. But the issue is that you have a limited amount of space in that connector. So it's real easy to solder in a 1/4 watt resistor. It's less easy to solder in a 1 watt resistor. So if you can solder in a 1 watt resistor and fit it in there, it'll last longer than a half watt or longer than a 1/4 watt. And so, you know, what it'll tell you, if you look at, like Adam Bennett's book, he'll say a 1 watt resistor, a half watt resistor. We used to say 1/4 watt resistor, but a 1/4 watt won't last as long as a half watt, and a half watt won't last as long as a 1 watt. So whatever size you can fit in there, that's, you know, the bigger the better, okay? That's a good point, Ray. So another cause of flicker or flashing is the refresh rate is too high. So if some hardware is slow and can't respond that quickly, so that's why it's a good idea to be able to change the refresh rate. Now, sometimes when you have long cable runs, you can have a difference differential in the voltages between here and there, and then you get ground loops. And also voltage can be induced from power cables, from fluorescent lights, from LED walls. Those can all induce voltage into the signal and cause ground loops. And if you have voltage that's more than 12 volts or minus 7 volts between the pin 2 and 1 or pin 3 and 1, that's what's called common mode voltage. And if it's too high, then that's going to mess up your data. So you can test for common mode voltage using an ohm meter. So if you take a voltmeter and you test between pins 1 and 2 or 1 and 3, if the voltage is more than plus 12 volts or minus 7 volts, then you know it's caused by this ground loop problem or the common mode voltage noise. So the solution is that on the receiving end, if you are able to disconnect the shield from the chassis, that will fix the problem. Now, fixtures are supposed to be designed that way. You know, the first version of DMX, they didn't specify. And so some manufacturers connected pin 1, when you plug in the data cable, it automatically connects to the chassis in the fixture. It's supposed to be floating there. Now that's the signal ground, not the safety ground. You're never ever, under any circumstances, supposed to lift the safety ground. That's the power cable green wire. That should always be connected properly, because otherwise you're putting people's lives at risk. But when it comes to the DMX cable, that's the signal. And that's the signal ground. On the receiving end, it shouldn't be connected to the chassis. And you can tell, you know, if you get a meter, if you have an ohm meter or a multimeter, and you put it in continuity mode, and you check for continuity between pin 1 and the chassis of the fixture, that'll tell you right away whether or not they're connected, and they should not be. Now, earlier we talked about how the console generates a packet of data. So this is an illustration of a packet of DMX data. Now, each of these values is an 8-bit value. The very first one we call slot 0. These are all called slots. Now, that's the technical term for it. Most people I know working shows and working with DMX, nobody ever calls it a slot. You know, just propeller heads like me do. But the fact is, those are technically, they're called a slot of data. The very first slot of data is labeled slot 0. And so what you're looking at here is the top number is the slot number. The bottom number is the value of that 8-bit byte of data. So slot 0 is the start code. That's what tells the receiver what kind of data this is. If the value in slot 0 is 0, that means it's a DMX packet. If it's not 0, then it's not a DMX packet. In this case, it shows it's 0, so we know this is DMX. The next slot is the value for address number 1. In this case, it's set to 128. Remember, it's an 8-bit byte, so there's 256 different levels of control. In this case, it's set to 50%, which is 128. Slot 2 in this case is set to 90. 3 is 255, 4 is 255, and so on, all the way up to 512. Now, after the controller outputs the value for address number 512, then it starts over, but first, there's a break. There's no activity on the line for at least 92 microseconds. Now, that timing has changed over the years. In the first version of DMX in 1986, it was 88 microseconds. And then in 1990, they changed the mark after break timing. And then in 2006, when DMX 512-A came out, they changed it to 92 microseconds. They extended it. They made it longer. So now there's a longer break between packets. And so after the break comes the mark after break, which is where the voltage goes high for at least 12 microseconds by today's DMX. And that signals the start of the next packet. And it just does this over and over and over again. So if you don't touch the values on the console, if you leave the faders alone, if you don't press the go button or anything, then it's going to continue to spit out the same values over and over and over again. Now, if something changes, if one of those values changes, it will be updated at the refresh rate. And as we saw, the refresh rate on the M series right now is 37 packets per second. So 37 times every second, the data is sent out again. New packet is sent out again. Now, every 8-bit value is framed by one start bit and one stop bit. Or sorry, 2 stop bits. One stop bit, two stop bits. So that means there's 11 bits in every slot. So this is a transceiver chip, and you saw those. We passed those around for you to look at. This is the old style with the through holes. You know, some of the older PC boards have holes drilled in them where you put the legs in, or it has a socket. Today, a lot of stuff is surface mount. That means instead of having holes in the PC board, there's pads that the legs sit on, and they're soldered to the top. That's surface mount. So, but they are 485 chips. And remember, 485 comes from the computer industry. That's a computer industry standard for serial data transmission. And these are differential line transceivers, meaning there's 2 inputs, not 1. So again, this is a symbol for an amplifier in an integrated circuit. It's called an op-amp. And there are single-ended op-amps. There are differential line transceivers. A differential line transceiver subtracts the 2 inputs. So one of the inputs is the actual data. The other is the data complement, meaning when the data goes high, the complement goes low, and vice versa. So that way, when you subtract the 2, it amplifies the signal, and it subtracts the noise as long as the noise is picked up equally on both lines. If it was a single-ended transceiver chip, it not only amplifies the signal, but it also amplifies the noise. So this is much better for noise rejection, and you get a quieter, cleaner signal. Now, in order to ensure that the noise is picked up equally on both lines, we use twisted pair wire. Because if it's not twisted pair, one of the conductors will be closer to the source of electromagnetic interference than the other, and you don't get full noise rejection. So by using twisted pair wire, we get better noise rejection. Now, RS-485, or DMX, is what's called a multi-point bus. That means that you can daisy chain the cable, which is a huge advantage, rather than having to run one cable to every fixture. You know, when I started in the lighting industry, when Jesus was a boy, the first movers that I saw, first moving lights I saw were analog fixtures. So that meant we had to run one cable to every fixture from the console. So, and the company I worked for at the time, we were installing sound lighting and video systems in nightclubs all over the United States. And so, if we had 2 weeks to install a system, we would spend a week and a half running cable, and then we have 3 or 4 days to finish the job. It's not fun. It's not easy. So DMX is a much better solution because you can daisy chain the signal because it's what's called a multi-point bus. That's the kind of topology that it is. It's a bus topology. The transceiver chip wants to be loaded to 120 ohms. That's why the characteristic impedance of the cable should be 120 ohms, because if the transceiver is loaded to 120 ohms, it thinks it's connected to an infinite length of cable. So also, these transceiver chips have a thermal shutdown circuit, meaning that if they're loaded incorrectly, they'll output too much current, they'll overheat, and if they didn't have thermal protection, they would burn themselves up. But they have built-in thermal protection. They'll shut themselves off before they burn up. Now, I don't know that I've ever seen that out in the wild in real life before. If a console stops outputting DMX, it's usually for some other reason. But it is nice to know that it does have that built-in thermal protection. Now, according to the RS-485 protocol, what it says is that you can connect up to 32 transceivers in a single link. So what that means to you and I is that you could connect, say for example, 32 moving lights in a single link, or you could connect, say, 31 moving lights and 1 fog machine, or if you're like me, 31 fog machines and 1 moving light, As long as you don't, you ought to see my shows, they're awesome. But as long as you don't connect more than 32 devices. Now, that is with a standard transceiver chip. It turns out that over the last several years, they have developed other kinds of transceiver chips that are called fractional load transceiver chips. Fractional load transceiver chips act like they only load the line to less than 1 unit. There are quarter load transceivers and there are 1/8 load transceiver chips. That means that if there is a fixture that has a quarter load transceiver chip, one fixture only counts as 1/4 of 1 unit load. That means you can connect 4 times as many fixtures in a single link as normal. Or if it's an 1/8 load, that's 8 times as many. That's either 128 or 256 fixtures connected in a single link. Now, up until recently, I'd never heard of any fixtures that actually had these in them. And then I was in Buenos Aires last year doing some training and troubleshooting at a large television studio there. And they had some ARRI L10 fixtures there. And so I was supposed to do a 3-day class. When I got there, they said, well, we've got some issues to work out in the studio. Can you do a 2-day class, and then we'll spend the 3rd day troubleshooting in the studio? And so to prepare for the troubleshooting, I went and I downloaded the user manual for the L10 fixtures, and I was reading it, and what it says is that with these particular fixtures, you can connect up to 128 fixtures in a single data link, single DMX link. And that tells you, oh, that is a quarter load transceiver chip. Now, those are the only fixtures that I've ever seen that actually have quarter load transceiver chips in them. And has anybody else ever heard of anything like that before? Yeah, I didn't think so.
So what's the advantage of that? Does it help with...
That's a good question.
Or is it just so you can have more?
It does not help with the signal. So Ray's asking, what's the advantage of having quarter load transceiver chips? I suppose if you get in a bind, and for some reason you need to connect more than 32 fixtures in a link, you can. But here's my view on it, is that I don't even like connecting 32 fixtures in a single link. I like to limit it somewhere between 4 and 8. Because if you lose one data cable, you'll lose a maximum 4 to 8 fixtures. Now, I can see there might be a scenario where I want to connect 128 in a single link. Say for example, and I've been in shows like this before, where you go into a giant arena and you ring the entire arena with truss, and then you put truss warmers in them, right? And so if you say you had 128 truss warmers that you just want to change the color of the truss, you know, so in that case, that is not mission critical. It's not key light, it's not fill light, it's not backlight. And if one cable goes down, you could lose up to 128 fixtures, but that's not going to be the end of the show. The show would still go on. It might not be as effective or pretty as you would like, but it's not going to bring the whole show down. So in an instance like that, yeah, maybe I might go for that. I might want to connect 128. Probably not, but you might. So that's the only application I could think of where I think it would be okay. Otherwise, I want to use data splitters. I want to split up those links for a lot of reasons. Okay. Now, according to the DMX protocol, the connectors are supposed to be 5-pin XLR, but as we discussed, there's lots of fixtures out there that have 3-pin XLR, and it works fine. The first version of DMX said pins 4 and 5 were not used. If you looked at the pinout, it would say NC for not connected. So a lot of manufacturers thought, well, hey, we can save some money if we use the 3-pin XLR instead of a 5-pin. And so that's why a lot of moving lights now still have 3-pin. Fortunately, I think it's good that a lot of moving lights now have both 3-pin and 5-pin, because you don't have to worry about what kind of cable I have, or do I need turnarounds. But either way, whether it's 3-pin or 5-pin, then the output is always a female, the input is a male. If you remember that, that will prevent you from having to rerun your cable and flip it over. You know, and I've done that many times, and I finally started remembering, but now you have to watch your crew, because as soon as you turn your back, they run it the wrong way, right? So now, here's the pinout for DMX today. 5-pin XLR, pin 1 is the shield. Then pins 2 and 3 is what we call the primary data link. And pin 2 is the data complement for the primary data link. Pin 3 is the true data for the primary data link. And pins 4 and 5 is an optional secondary data link. So pin 4 would be the data complement, pin 5 is the true data for say for example, you want to have a second universe of DMX on pins 4 and 5. You're allowed to do that according to the DMX protocol. And in fact, Avolites did it with their Pearl consoles from 2010 to 2006 to 2010. So if you have a Pearl console, a 2010 console or something like that, then you can send a second universe of DMX on pins 4 and 5, which means at some point you're going to have a breakout to physically separate those two universes to go to their respective fixtures. They stopped doing that. And as far as I know, I don't think there's any other manufacturers who use pins 4 and 5 at all. So we're still using, the same pins 2 and 3 to send DMX that we always have. Sorry, what's your name again?
John.
John.
Elation did have a splitter that did basically a Y connector, essentially, that they were selling to use with the CompuShow box, because you could actually do 2 universes out of one of the CompuShow ports. Okay,
so what John is saying is that the CompuShow is a controller that runs on a PC, it's software-based controller, and in order to get DMX out of your laptop, it had a USB to DMX dongle, and there's two ports on it, I think.
There's actually, there are 2 physical DMX ports on it. One was a 3-pin, the other was a 5-pin.
Okay.
And out of the 5-pin, you could get 2 universes. So in total, you could actually do 3 universes of DMX.
Ah, okay. So he's saying on the 3-pin, you got 1 universe. Yeah, and on the 5-pin, you could get actually 2 universes. So do they still do that?
They do, yes.
Okay, there you go. See, I learned something every time I do one of these classes. And I don't know what happened to it, but we had that box earlier today.
Blue box that had the DMX chip?
There you go. That's what he's talking about right there. That is the, what's it called again? The
CompuShow.
CompuShow, thank you. Yeah, CompuShow. Okay. Good to know. That's good to know. And there's a note in here that says the shield must not be connected to or in contact with the shell or body of either the male or female connectors, because chassis-mounted connectors are generally connected to mains ground, which could cause ground loops, which can corrupt the data. Okay? Now, once again, we already talked about terminating your data runs, but this is from Adam Bennett's book, Recommended Practice for DMX 512. He says, always terminate your data runs. That means that when you set up your fixtures, you daisy chain the cable, you take a data terminator, and you plug it into the last fixture in the run. It's a very quick, simple, inexpensive thing to do. Maximum of 32 loads per link. Now I say must be EIA 485 compliant, because there is some gear that does not comply with DMX. And then of course there's some gear that uses fraction load transceiver chips, although it's very, very rare. As far as I know, that fixture, the REL10 series, is the only one I've ever seen that does that. Their L7 doesn't do it, their sky panels don't do that, just the L10s. No Ys or parallel connections. If I take a data cable and I cut it and I wire it together and make a Y, then what I've done is I've taken a 120 ohm cable and I've paralleled two 120 ohm cables together, which makes a 60 ohm interface. So now I have a 120 ohm cable and two cables that make a 60 ohm network, and there's an interface between the two. So what happens is when the console sends the data down the line, when it hits the Y, some of the signal goes through, but some is reflected back, and then you get reinforcement and cancellation, and it can corrupt the data. So that's not a good idea. Okay, so no Ys. And this just explains why you shouldn't have a Y. And again, this comes straight out of Adam Bennett's book. So now, what do you do instead of Y? What if you want to split the signal? Well, you use a data splitter. And a data splitter can extend your run because it regenerates the signal, and now you've got another 1,000 feet or whatever. It also starts your count over, so now you can have another 32 devices for each of the outputs. And it also makes it easier to install a system, and it's easier to troubleshoot because it's going to narrow down any problem you have to a smaller group of fixtures. If you just link your fixtures all together and you lose a data cable, who knows where the bad data cable is. But if you use a data splitter, it's going to isolate it to a single output, and it's much easier to troubleshoot that way. Now, yeah, Ray?
I was just going to say, if you go back one shot, you need to,
Whoop, sorry. Let me get past this. Right here.
yeah, don't forget, all of those outputs are going to need terminators.
Okay. So what Ray is saying is that in a data splitter, if you don't have something plugged into it, each of these outputs needs to be terminated. Now, I could be mistaken, but I believe that depends on how the data splitter is built, because if it has isolation, I don't think
all
you.
of those are opto-isolated.
Okay, yeah, and you still need to terminate them all. Okay, all right, good enough. Now, yes, question?
What if the splitter has a terminator on it?
You mean like a termination switch?
Yeah, like that little button next to the.
Right here?
Yeah.
Yeah. So that terminates them, right? So yeah.
You no longer need the terminator.
That only terminates
The through.
the output.
Oh, the through, yeah. So you have an input.
And an
No,
output.
that's a 3 and a 5 pin.
First one's a through, I think. Because the first one works whether there's power or not. That's just a through.
Okay.
So that would terminate just that one.
Oh yeah, here's the input, here's the output. Yeah. So that terminates that. Yeah. Yeah. So he's talking about all the rest of them.
The rest of them
Yeah.
would need a terminator.
If there's nothing plugged in.
Don't need.
I thought it did.
Well, he's saying it does. So
I thought you said it did.
We'll get clarification on that. But
Yeah,
my understanding of how it's done in that, because it's
optically isolated.
Thank you. Got it. Not today.
Yeah.
There is no signal going back in through the ports that are not used.
Right.
Because there's no physical junction.
Exactly.
Why we decide to do
Exactly.
The
Yeah.
optical. The cheaper ones that are out there, so, and you can't tell just from the box itself. You have to know your manufacturer, because some of those are just hardwired
Right.
jumpers, which would allow for the signal to go back. But
Right.
if you're using an opto,
Yeah.
it's a light beam, so there is no return.
So I agree with Ray, and what Ray just said is that whether or not you need to terminate every output if it's not being used depends on how the unit is built. If it has optical isolation, then in my opinion, and we're going to double check this, that you don't need to terminate every output. You only need to terminate them all if it's not optically isolated. We will we'll get back to you on that. But I've always understood that optical isolation will prevent signal reflections back down the line. Okay, and so it turns out that not all data splitters are actually optically isolated, and not all devices that are optically isolated are data splitters. Optical isolation is a means of protecting sensitive electronics, and here's how it works. Suppose you have a fixture and you're feeding it DMX, then the first thing it's going to hit, the cable is going to feed a signal to the transceiver chip. And the output of the transceiver chip is connected to another integrated circuit chip called an optocoupler chip. An optocoupler chip is an integrated circuit chip that has an LED at the input and a photoreceptor at the output. So what happens is that when the data goes high, the transceiver outputs voltage that turns on the LED, and the photoreceptor senses it and it outputs voltage. If the data goes low, then the transceiver turns off the LED and the photoreceptor does not output voltage. So the output of the optocoupler chip exactly mimics the output of the transceiver chip, except there is no electrical connection between the input and the output because it's optically isolated. So what happens is that if you get a lightning strike, then the voltage of the whole building is going to rise and fall, and because the shield's connected to building steel, then voltage will get on the cable. It can destroy the transceiver chip. It might even destroy the optocoupler chip, but it will protect all of the expensive electronics downstream from the optocoupler chip. And that means the motherboard, the CPU or processor, the RAM, the ROM, all the memory is all protected, and that's what costs most money. So these are sacrificial devices. The manufacturers know they're likely to fail, and so they make them easy to replace. Okay? So if you look at the schematic, it makes sense that if you have optically isolated outputs, then I don't think that signal reflections could work their way upstream and then back downstream through your terminated outputs. So that's why, in my opinion, you don't need to terminate open ports on data splitters if the data splitter is optically isolated. But remember, not all of them are optically isolated. People often refer to these as opto splitters. Some of them are, some of them are not. Sorry, what's your name again?
Daniel.
Daniel.
Are opto splitters the only places where you'll find the optical isolation?
No. In the early days, there were some fixtures that were optically isolated. I don't see that much anymore. But there are other, there's all kinds of devices that have optical isolation in them. The more expensive it is, the more likely it is to have optical isolation, you know. Okay? Oh, there's your, these are examples of optocoupler chips. They just look like a regular integrated circuit chip, but very much like the transceiver chips. Okay? So, continuing with best practices, maximum recommended run, 1,000 feet. Now you saw a little bit more detailed information. That depends on the wire gauge. So 1,000 feet is based on 24 gauge wire. If you have bigger than 24 gauge, like 22 gauge wire, then according to Adam Bennett, you can go even further, 1,600 feet. But I would say this, you know, that book was written several years ago before wireless DMX really started gaining ground. Today, I feel like if you need to go 1,000 feet, then it's probably better and easier, faster to use wireless DMX. Now, we're going to talk more about wireless DMX a little bit later on, but just remember that. Keep that in the back of your head, okay? So, now when you route your DMX, and this goes for any signal cable because they're susceptible to electromagnetic interference, you want to route them away from power cables. And I say especially dimmed power. If you have dimmers, you know, the power lines feeding the lamps, what happens is that when you dim a load, then you're creating, the current waveform has sharp edges in it, which is an indication of higher frequency current. And the higher the frequency, the further the electromagnetic radiation radiates. And so when you dim loads, then it generates all kinds of electromagnetic interference. So if you have your DMX cable or any signal cable for that matter close to that, then it can very easily induce noise into the system, more so than the transceiver chip, than the differential line transceiver can reject, and you could have problems. Yeah, question?
So we have a couple of ferrite chokers in our units. Does it depend on where you put the ferrite choker on the line?
No, because, so, sorry, what's your, huh? Zach, that's right. So what Zach is saying is that he has some equipment with ferrite beads on the power cable, and you may have seen these before. It's a magnetic donut that goes on the power cable, and it's designed, yeah, like that. So if you were to open that up, you'd find a ferrite bead. Ferrite is magnetic material, and the whole idea is it absorbs electromagnetic radiation. And Zach's question is, does it matter where along that cable the ferrite bead is? And the answer is no. It can be anywhere on that cable, and it just absorbs it reduces the amount of electromagnetic, it doesn't completely eliminate it, but it reduces the amount of electromagnetic radiation, okay? And also, for permanent installations, you don't want to run the DMX cable in the same conduit as power cables, because that's putting your power cable right next to your signal cable, and that can cause noise to be induced into the DMX cable as well. Okay. Now we talked a bit about ground loops, but ground loops can interfere with lighting control just as much as they can interfere with audio. And it happens when the pin 1 is, when you plug in your cable, pin 1 is a shield. When it's connected on both ends from the console and the fixture, now you've created a conductive loop that goes through the shield, through pin 1, through the chassis, to the green grounding conductor in the power cable, back to the other chassis to pin 1 in the shield. And so that's a complete loop. So the only thing you need for current to circulate in that ground loop is a source of voltage. And the voltage is induced by the power cable, because the anytime you have current flowing through a conductor, there's a magnetic field around it. And the power cable is conducting current to the device, and it generates a magnetic field. And because it's alternating current, the magnetic field is expanding and collapsing 120 times per second, which means the lines of flux are cutting across the conductors, which generates a voltage and causes that ground loop current to flow, and that can interfere with your data. So the solution is to disconnect the connection between pin 1 in the receiving end, the fixture, between pin 1 and the chassis of that fixture. That's what we call a telescoping shield, because the shield telescopes from the transmitter to the receiver. Now, Adam Bennett, this is a pin 1 check. If you want to check real quickly whether or not your fixture has a connection between pin 1 and the chassis, all you do is you get a multimeter and you check to see if you have continuity between the pin 1 on DMX and the chassis of the fixture. So I travel with where's my meter? Here we go. So I travel with the Fluke multimeter. This is a voltmeter, an amp meter, and a resistance meter or an ohm meter. And so if I wanted to check, I would put my leads in the meter. And then there's a mode selection switch here, so I'd put it in continuity mode. And so to check for continuity, when you touch the leads together, it beeps. So that means that there's continuity. So I could check for continuity, for example, on this fixture right here. Between pin 1 and the chassis. Let's see if I can, I don't know if there's enough light, but I'm going to check it real quick. So pin 1's in the middle, that and that. And there's no beep, so this fixture has no continuity between pin 1 and the chassis, that's the way it's supposed to be built. That helps prevent signal problems. Now you can also do the same thing to check for common mode voltage by using a voltmeter, and you check between pins 2 and 3. So in the old days, to set the DMX address on a fixture, they had dip switches. Now fortunately we have menus now. They're much easier to set the DMX address. But if there's still some fixtures and strobes and fog machines that have dip switches. So if you have to set the DMX address using a dip switch, it's a binary number conversion. You know, every switch is a power of 2. And if you know how binary counting works, you can set the switches on or off to match the address. The funny thing about dip switches, you know, when you walk into a room and you flip the switch up, that's the universal position for on, right? But for some reason, manufacturers that use dip switches, they like to put them in upside down. So down is sometimes on and up is off. And then the other quirky thing about them is that if all the switches are off, that's a binary number 0, and there's no DMX address 0. So some manufacturers say that's not a valid DMX setting, but others say that is DMX address number 1. So you have to know which is which. So sometimes you have to go to the manual or look on the side of the fixture and it'll tell you. Okay? Now there are dip switch calculators to help you with this, you know. So there are free apps you can download on your smartphone, and it'll tell you, you know, you punch in the DMX address, it'll tell you which switches to set. So that's kind of handy to have. Here's a short list of them, but there's a lot more of them now. So some of them are free, some you have to pay for, some are good, some okay. All right. Now DMX 512-A is the current protocol for DMX. The dash A came out in 2006. But honestly, you know, there's very little difference between DMX 512-A and the DMX that came out in 1986. They're almost the same. There are a couple of variances, but for the most part, they operate pretty much the same, and it's all backwards compatible. So what they changed in 2006 is they allowed the use of alternate start codes. So that very first slot of data, slot 0, before 2006, there was only one valid setting for that. That was 0, and that means DMX. Today, there are other start codes, the most common of which is hexadecimal CC or decimal 204, which means this is an RDM packet. So it's either a DMX packet or an RDM packet. Now there are some proprietary start codes, but I've never encountered them before. So the only two start codes that I know are in use today are DMX and RDM. Secondly, in 2006, they said, okay, if you want to do something with pins 4 and 5, like add a second universe of DMX, you can. So they have optional uses for pins 4 and 5, but again, very few manufacturers are actually taking advantage of that. Avolites did, and apparently what's it called? CompuShow. Yeah, CompuShow does that as well, but those are the only two that I've ever heard of that do that. And then they also did something called System Information Packets, or SIPs. And that's just basically a way of testing the network to make sure that your DMX is working. I've never used this before. I think you have to have a specialized controller, like a little DMXter, to be able to use that. But I just use handhelds to do that. Yes?
If I remember correctly, Very Light actually used pins 4 and 5 to provide a talkback feature in the VL3000 and 3500 line. So if you plug them all in together and did a startup procedure, it would actually send a signal back and forth through the daisy chain and check the starting software on all of them.
Okay.
And automatically update to the new software.
So what John is saying is that he believes that in the Series 3000 Verilites, that it uses pins 4 and 5 for a proprietary application where it checks for the software version to make sure they're all matched. That's important, you know. When you have a big rig with a lot of, every model, every fixture of the same model should have matching software version numbers, because if they don't, then they could behave differently. So you need to go, you know, when you're prepping a show, you go pull all the gear, and then all the same models, you need to check the software version, make sure it matches. So what John is saying, that he believes the Series 3000 Verilites will use pins 4 and 5 to automatically check the software version to make sure they match. I wasn't aware of that, but that's good to know. Okay. So testing and troubleshooting again. According to Adam Bennett, nearly all the problems with DMX are due to cable faults, poor cable layout, or interference. And there are also some products in the market that don't conform exactly to the DMX 512 specification. And you do find that occasionally, which is why it pays to have some DMX testing tools. So you can find out, is it the fixture? Is it the console? Is it the configuration? What exactly is causing this problem? Okay, we're going to talk about RDM, or remote device management, but first let's take a 10-minute break.